Well, this is the second part of Tuesday's lecture, and we're going to start with doing more on section 5.1. So chapter 5 is called Control Volume Analysis, and that's where we make some sort of rectangle or shape and analyze flow in and out. It might better be called inside of a device analysis, because that's usually what it's used for, where a device is a very broad term. If we analyze in a fan, like I showed you earlier, well, we're going to have air coming into the fan and air coming out of the fan. And we're wondering on what goes on with that air as it goes through the fan. And we would draw a dotted line to represent the exterior of the fan and think about all the fluid that crosses the fan boundary or control surface. Well, this is a device, and we're taking a look at basically at what's going on once we cross the boundary inside the device, both in and out. The same thing could be true for a compressor, a pump, a turbine, a section of pipe, a nozzle, a diffuser, etc. So if you see this letter CV, you could translate it roughly as inside a device, and almost always be correct. All right, so just on 5.1, section 5.1. Last time we got going on it, in short, what we're going to do, the first in-out analysis we're going to do is mass flow rate. And I summarized it by m dot n is equal to m dot out. And I got these letters SS. That's at steady state. It's not necessarily true that for something mass flow in and mass flow out are always equal. For example, if you're filling a tank, some sort of tank, and you're filling it. Well, while you're filling it, there's only m dot in and there's not m dot out. That's not there. There's no balance there. But many of the devices we're going to do, we're going to analyze in steady state. We're going to stick with that for now. Just be aware of that. Okay. Briefly on section 5.1, finishing it off for today, I want you to be aware that in this analysis, m dot is not treated as a vector. Okay, so a vector has magnitude and direction, and we're just a scalar. We're just worried about the quantity. We're not saying whether it has a direction or not, and that's a really important idea. So let me give you a couple examples to think about that. Okay, so there's a pipe bend. There's a lot of fluid systems where fluid makes a 180 and makes a turn, okay? And if the numbers worked out for this flow, just making it easy, then we had something like 3 kilograms per second here and 3 kilograms per second there, okay? I could see a student thinking, I'm gonna call this point 2 over here like this, and this point 1. I could see someone saying, hey, m dot 2 is not equal to m dot 1. Because they would be thinking, well, m dot 1 is plus 3, is to the right, and m dot 2 is negative 3. And negative 3 doesn't equal plus 3. Well, how are they treating m dot in that case? Are they treating it as a scalar or a vector? They're treating it as a vector because they're saying that this m dot is a negative number. They're taking into account direction. But our analysis instead is going to be as a scalar, so we're going to say the in is equal to the out. Okay. Another quick example like that. There are lots of devices out there like T's or converging devices where we take two fluid flows and have them enter. So this could be a mixing box, a little bit of an unusual mixing box. But a mixing box takes two fluid streams, brings them together, okay? And then they mix inside here like this, and then they're going to go on out. Okay, and I could see in this case a student saying, oh, that's going to be 5. That's going to be 5, because we have some sort of triangle we can draw here where we have 3 going this way and we have 4 going that way. And so the hypotenuse is going to be 5. Well, just to be sure, get the right number yourself. What does that number have to be? Okay, if you're getting 5 over here like this, well then once again, you're treating this like a vector. You're treating these mass flow rates in like vectors. But again, we just treat them as scalars. And so in this case, the answer is 7. And of course, that makes sense to us. This is saying every second 3 kilograms of this fluid comes in, every second 4 kilograms of this fluid comes in. For it to be balanced, every second 7 kilograms have to come out. All right, so m dot needs to be treated as a scalar, not a vector. A really important idea. All right, quick aside before we move on. You may be wondering about test 1. I had it on the preliminary schedule for Monday of next week, but with things going on, I think, I appreciate everyone's dealing with the challenges that I've been facing. I think we're going to do it Tuesday, June 16th. So some things about it so you can start thinking about it. It'll be based on homework number 1 through 5. Number 1 through 4, you have all those. Number 5, I'm working on getting together. Number 5 will be relatively short, okay? So don't be intimidated by it, just get going. It'll also be, as far as lecture material, it'll be through Thursday's lecture, which I should be getting posted to you guys soon. I believe I'm going to make it very similar in format to the quiz, which may be intimidating for some of you, but I think with a little bit of thought and planning, you're going to get a little bit more comfortable with it. So that's going to be a combination of some short problems where you just work it out and enter the answer in a box. And that is great practice. Many of you are going to want to take the FE exam, and the FE exam, it's right or wrong. Not a lot of those, but I feel a few of those are really good for you. And then there'll be likely 3 or perhaps, if shorter, 4 written out problems. And these are likely what it will be for the written out problems. The longer problems, where there'll be multiple parts, you write out your work, you get partial credit. A manometer. A Bernoulli problem, where a fluid moves from point 1 to point 2, and you use the Bernoulli equation. A velocity field problem. That is on homework number 4, and I'll give you more practice on homework number 5. And then a problem on control volumes involving some ideas from section 5.1 and 5.2. Section 5.1 and 5.2 are very large. The stuff you're going to be responsible is just stuff on homework and Thursday's lecture. And if you can follow what we're going to do, or today and Thursday's lecture, if you can follow what we're going to do in a few minutes, you're halfway there to understanding how to do the section 5.2 type problems. All right, so let's get going on 5.2 and try to get some of the basics up there. So 5.2 in short is going to be involved using this computation as a step along the way to figuring out forces. Forces on pumps, forces on nozzles, forces on U-bends. And let's sort of talk about, just to get going, what the forces might be like. So there's a U-bend as part of a piping system over by our house, a huge piping system. I mean, these pipes are like about 9-inch diameter. That doesn't sound very large, but a 9-inch diameter pipe is pretty large. It carries a lot of water. I don't know exactly what it is, but not atypical would be something like 200 GPMs of water. Okay. Well, water is largely incompressible, and if we were at steady state, there would be 200 GPMs going on. Okay. And part of the thinking in section 5.2 is taking a look at our fluid that goes through a device and say, hey, what is the net force on that fluid? What is the net force on that fluid? And what I'd like you to do is just take a pause for a second and say, hey, is that net force going to be to the right or to the left? Okay, well, the fluid is coming this way and its leftward motion is stopped. That's going to take a push on it to the right. And then it gets turned around and starts going to the right. So this motion is stopped, and then this motion is created, and that takes a force to the right. So the net force on the fluid is going to be the right. By the way, very shortly, with a little bit of work, we're going to be able to calculate that. And it might turn out to be something pretty large, like 250-pound force, 250-pound force. Okay, so basically, when we're done with our preliminary analysis on section 5.2, we are going to be able to say something like, hey, the force on the water that passes through this device, The book's going to use the word control volume. It's the interior of a device. It's going to be 250 pounds. So then you might say, well, so what? You know, that's a calculation, but as an engineer, what good does it do me? Well, that basically is going to be, in part, the force of the U-bend on the water. It's this U-bend piping that pushes on the water. So I want to be very careful about this because this is not complete, but as a good partial step, we could say that the force of the U-bend on the water is 250 to the right. Okay. Keep in mind that these problems we're going to do will involve Newton's third. That's very important, Newton's third law. So what does Newton's third law say? Newton's third law says that for every action, there's an equal and opposite reaction. And that's not very helpful. I don't think that that phrase really clarifies what's going on. But thinking about it, trying to clarify what that means actually, you can think about all sorts of examples, but maybe something like boxing. So like if a boxer's fist hits someone else's face, well, maybe I should use a different word. I'll use cheek. There would be a force of fist on cheek that way. Okay, what does Newton's third law say? There is going to be a force of the cheek on the fist the other way. So my fist pushes on the cheek that way, the cheek pushes on my fist the other way. If I hit with a 100-pound force like that, okay, what is the force of the cheek on the fist? Also 100 pounds. It's exactly equal and opposite. That is an empirical law that was observed as Newton tried to figure out, hey, what's going on in the world? Can I understand motion? Can I understand forces? It is always true. There is no boxer in the world that is so skilled that she or he can hit with 150 pounds force and not be hit back with 150 pounds force. Always true, Newton's third law. Well, let's apply it to this diagram. Okay. So if there's a force of the U-bend on the water, 250 pounds to the right, then, well, in some physics books, the notations from Newton's third law then just takes these subscripts and reverses them. What would that stand for? That would stand for the force of the water on the U-bend, and that would also have to be 250 pounds to the left. Okay, so this water, as it goes through, okay, in the net, it ends up pushing on the U-bend. All right. Well, that U-bend that's out by my on a device near where I live, and there's all sorts of U-bends out there in the world. It's got to be anchored. Okay, it's got to be anchored. So there might be an anchor here like this. There might be an anchor here like that, and there might be an anchor here like that. Hey, if you're engineering a system, how strong do those anchors need to be? Well, they need to be able to withstand a 250-pound force. So if you're the one who's responsible for specifying the bolts that go through and attach that anchor to the surrounding ground or the surrounding surface, then you know what force you have to come up with. So where we're headed is we're trying to figure out forces on fluids. It's useful though, because that allows us to figure out other forces in designing systems. Okay, hey, no need to copy this down, but I'd like to give you a preview of where we're heading. In chapter 5, there are a lot of control volume problems where we compare something going in versus something going out, flow in, flow out. So we already did mass flow in, mass flow out. That's section 5.1. We have more work to do on 5.1, but I'm going to save that for another day, and that's not going to be on test. That's not going to be on test 1. Okay. We can also do energy flow in, energy flow out, entropy flow in, entropy flow out. Okay. But for force, it turns out what we're going to do is we're going to take a look at mass flow in and speed in and mass flow out and speed out. And we're going to compare m.1 v1 to m.2 v2. Okay. They are not necessarily going to be equal, and that's going to be part of our analysis. I'm going to spend a few minutes going on some background. I'd like you to know where we're headed. We're going to do this calculation. Eventually, we're going to do this calculation, and do a comparison. All right. Well, if I'll ask you to look through a little bit of material in chapter 5, do some brief reading to supplement what we have in lecture, and you're going to see this term a lot for section 5.2, linear momentum flow, either into or out of a control volume. So here's a control volume, interior of a device, and there's going to be some linear momentum flow in. So the first thing I want to do is think of what kind of units that would have. I'm going to add something to the drawing though. Let's imagine we got this blob of fluid here, okay? And then there's another blob of fluid and another blob of fluid, and those blobs are entering in there like that, okay? And each blob is going to have some linear momentum associated with it that gets carried in. And what kind of units would be the linear momentum flow, or the rate that linear momentum flow goes in? Okay, so just a quick side analysis that I would write down. I mean, what if we did energy flow? Okay, not writing that down, thinking about it. What kind of units would that have, flow of energy? Okay, well, energy, say in SI units, has joules. And if we're wondering about the rate that energy goes in, it would be joules per second. And of course, some of you might be saying, hey, I could make that into watts. Great. But the bottom line is this would be joules per second. And how did I get this? I thought about the units for energy, then I made it into rate. Okay, what about units for momentum? Okay, how do we work out the momentum of something? Well, the momentum of an object, you guys have done that in Physics 11a, and some of you will do that in dynamics. If I have some mass and I have it going along with v, how do we quantify its momentum? It's essentially, in a way, how hard it is to stop. And how hard it is to stop depends both on its mass. A moving elephant is a lot harder to stop than a moving ant, and also how fast it's going. So momentum is mass times velocity. Okay, what about those units? What would those units be? Okay, so that's a reminder. The momentum of an object is its mass times its volume, velocity or speed, and that an object could include a blob of fluid. Okay, well, an SI, okay, erasing this stuff over here, kilograms times meters per second, so kilogram meters per second. Okay, in BG, okay, mass is instead of slugs, speed is feet per second, so that would be slug feet per second. Okay, units for momentum. By the way, is momentum a vector? Absolutely, momentum is a vector, so it has a direction. So, a vector. Okay. All right, but it turns out that what we're going to be interested in for control volumes and when we're doing force analysis is momentum flow. So how about units for momentum flow? Well, just earlier I did energy flow. Energy is joules, and flow or rate in would be joules per second. Okay, well in SI, we would be wondering a unit of momentum is a kilogram meter per second. We would wonder how many kilogram meters per second actually flow in. Okay, how many kilogram meters per second flow in? So, you know, please don't write these numbers down, but to take an example, if each one of these blobs has momentum 4 kilogram meters per second, that's 4 kilogram meters per second, sorry, it's a little bit small, each one of these blobs, and there are 5 per second coming in, well, then we could work out how much momentum's coming in. And the bottom line, what I'm trying to drive at here, is the SI units would be how many kilogram meters per second are coming in per second. Kilogram meter per second. Okay, see, remember in so much of your physics we've done, we don't like writing things as compound fractions. So see if you could write it as a single fraction. Okay, so that's going to be a kilogram meter per second squared. Okay. And in this case, it turns out it's very useful to remember what another word for a kilogram meter per second squared is, and that's a Newton. Okay. All right, hey, let's do one more. Let's do BG. We could do the EE system, but in this case, BE, SI, and BG are going to be good enough. Okay, so momentum flow, it would be a unit of momentum would be slug feet per second. We could have 4 slug feet per second or 30 slug feet per second. And then we're wondering the rate at which those slug feet per second come in. So we would have slug foot per second. Okay, so that would be the BG unit for momentum flow. And then if we're simplifying it, that's going to be slug foot per second squared. And once again, it's useful to remember what a slug foot per second squared is, and that is a pound. Okay. So please don't copy this down, but just to get a feel for what's going on, we're going to look at control volumes. And we're going to compare momentum flow in, and we might get something like momentum flow in if we were in SI units of 40 newtons. That means there's fluid coming in, and if we quantify the momentum flow, we get 40 newtons. And then we might get momentum flow out, and we might get something like 50 newtons, okay? And wow, those are units of force. Well, it turns out it relates to force. We're going to say there's more momentum flow in versus out, and that's going to tell us something about what's going on with the fluid in the control volume. All right, so earlier I talked about, just a minute ago, calculate what units would be for linear momentum flow, say in. We could do it in or we could do it out. How are we going to actually quantify it? What about a fluid flow is going to allow us to calculate linear momentum flow in? Is it going to be, say, 40 kilogram meters per second, or 40 kilogram meters per second squared, or 400 kilogram meters per second squared? Okay. Well, obviously, it's going to have something to do with how fast the fluid is moving. But let's get down to actually how you go about doing it. So for some students, I think it's helpful to think about how you would do energy flow in. So I wouldn't write this down, but try to follow what's going on. So for energy flow, if we were trying to figure out if we have some sort of stream entering a control volume, or again, a control volume might be some sort of device, okay? At what joules per second, okay? At what joules per second is energy being brought in there, okay? And it turns out, as many of you have seen in Engineering 124, and is a big part of your engineering education here, what we can do is we can imagine essentially these blobs of fluid coming along that are going to enter, okay? And we can, what we do actually is we think about the fluid that's entering, what is its energy per unit mass, okay? What is its energy per unit mass? Again, this is not part of our responsibility right now in the class, just trying to give you a background to think about. Let's just say, just to make the numbers easy, let's say that this fluid that's coming in, maybe it's water, has energy 10 joules per kilogram. Okay. Y lowercase e, this is specific energy per kilogram. Something else that we could easily classify or probably characterize about the fluid would be its mass flow rate. Okay. And let's say it turns out that the mass flow rate is 5 kilograms per second. Okay, well, hopefully you can pause for a second and put those two numbers together and get the joules per second that are entering that control volume associated with these numbers. All right. It turns out it's 50, and hopefully you can reason your way through it. Every kilogram that comes in has 10 joules, and there are five of these kilograms coming in per second. Just logically, it's 50. And what we do in this case is we take the mass flow rate times the energy per unit mass. Something that you'll do a lot in Engineering 124, in ME128, in ME126, and of course in this fluids class later in the semester. And the point that I'm trying to drive at is we did, to get the rate that energy flows in, we did m dot times the energy per unit mass. Okay, so what we're going to do here, now we're trying to do linear momentum flow in. We're going to do m dot times the momentum per unit mass. And that I don't think you need to write down, because this equation we're going to get is very simple, but I'd like you to make sense of it. Okay, so how are we going to calculate momentum per unit mass? If we could come up with an expression for this thing here, then linear momentum flow is going to be a piece of cake. All right, so now we're getting ready to go. We're trying to get momentum per unit mass. Okay, so putting a number on the board. Okay, I claim that we know that that tells us for the, if this fluid is entering at 5 meters per second, I claim that that tells us the momentum per unit mass. Okay, momentum per unit mass. All right, well, let's just think about it really quickly. Momentum is mass times volume. speed. Momentum is mass times speed. So momentum per unit mass would essentially be P over M, and that would be speed. So speed tells us momentum per unit mass. And you can see it, from these units right here. Okay, momentum, if you thought about the units over here, momentum is kilogram meters per second. So momentum per unit mass would be kilogram meters per second per kilogram. In other words, meters per second. So how would we quantify, or how would we express momentum per unit mass? It's just going to be the fluid average speed, or I'm just going to do V, okay, which be the fluid average speed. By the way, some units that you're going to see, okay, it turns out that just like the vector analysis we did earlier, okay, when we had a velocity vector, U is oftentimes, and in chapter 5, used for the speed in the speed in the horizontal direction. V is used for the speed in the vertical direction. So sometimes we're going to see m dot u, and that calculation would tell us momentum in the x direction. And by the way, momentum flow is a vector, all right? And m dot v, that's going to tell us momentum flow in the y direction. All right, kind of a mess on the board. Let me try to summarize what it is that you need to know. Okay, what you need to know is that to calculate linear momentum flow, okay, in or out of a control volume, you're going to do, in general, m dot times v, okay, where this is fluid average speed. I'm just going to write fluid speed for now. We know that if fluid moves some sort of pipe, we got a no-slip condition at the edges, and so the fluid in the middle might be going faster at the edges, but for right now, we're just using the average speed, okay? We could also calculate it using m dot u, and that would be horizontal momentum, and we could also do m dot times v, and a lot of times that's going to be vertical. They're all the same, they're all going to be the same calculation, and note that linear momentum flow is a vector. They have magnitude and direction, all are vectors. All right. So we'll do a few quick examples just on that basic calculation. This one I want to copy down. Hey, go ahead and take a look at that situation. Figure out the linear momentum flow. Come up with the number. All right, so linear momentum flow is m dot times speed. M dot times speed. In this case, I could use m dot, instead of m dot u, I could do m dot lower v, but that's not a big deal right now to me, and eventually you'll get comfortable what to use. All right, so as a good start, if someone wrote 20, hey, that's about a C right now, C level work, okay? We gotta get the units, and it is a vector, so we need to get the direction. So units are going to be kilograms per second times meters per second. So you could do that as kilogram meters per second squared. That probably would be the most meaningful units, okay? Although if someone wrote newtons, a kilogram meter per second squared is equivalent to a newton in this case, but I don't have direction. So in this case, maybe you could either say that it is 20 kilogram per meter second squared negative in the negative y direction, or we could say down. Okay. All right, good. This one's probably worth copying down, okay? A lot of times our information is not m dot v. Like I've said before, out in the field, a lot of times you don't have measurements that actually give you m dot, but you do have measurements that give you volume flow rate. So let's imagine this is some sort of device. It's a device that handles air, and there's some air that's flowing in. And fairly easily, we could get a measurement of volume flow rate, and also we have the speed going in. Why don't you go ahead and get the linear momentum flow in if it's air, and let's assume that it's air at the standard values, so we don't have to use the ideal gas law, so we can use the tables. Go for it. Okay, here's the work for A. we need m dot times v. This is volume flow rate, so we need to convert it into mass flow rate. One basic relationship you're going to get good at is if you are faithful about doing the homework. And the standard density of air at normal temperatures and pressures is a good 1.23. So I get that m dot is 1.23 kilograms per second. So a non-trivial amount of mass coming in. What's the linear momentum flow in? Okay, it would be 1.23 times the speed of 10, so I get 12.3. I can do that as kilogram meters per second squared or newtons, and it is to the right or in. All right, let's just compare how it is for water. This should be fast now. What if instead that fluid was water? Hey, before you get going on the calculation, wouldn't the numbers, you might think, wouldn't the numbers be very different for water? But it turns out that many times the speeds in systems for water and for air are not unsimilar. So these two numbers, this could be a number for air and it could be a number for water. In addition, sometimes the volume flow rates are somewhat similar as well. So it's not inconceivable that we could have these flows for water as well. All right, well, hopefully you got it. The mass flow rate is going to be the density times the volume flow rate. And if I go to the standard values for water, I can use 1,000. So the mass flow rate is 1,000 kilograms per second. Wow, that is a ton of mass coming in. But once again, water is much more dense than air, so that's going to be a ton of mass going in. Okay, and what about the linear momentum flow in? Okay, it could be m dot v, or if we were thinking about a coordinate axis, we could do it as m dot u, just similar symbols. Okay, and we're going to do 1,000 times 10, and we get 10,000 newtons to the right. Okay, and this calculation is going to have something to do with force. Hey, that is a heck of a lot of water moving pretty fast. There's going to be a lot of force involved. All right, let's get the basic equation up there. So I won't copy this stuff down in red, but it's worth me explaining for just a little bit. Okay. What we're doing in chapter 5 is we're comparing in and out. So this might be control volume and we're comparing in and out. And there is an equation comparing in and out that allows us to get the net force. The net force of what? The net force of the fluid going through the control volume. So the net force on the air, or the net force on the water, or the net force on the engine. Okay, 5.21 is a very nice general statement. And it is expressed both verbally and using calculus to give a complete analysis. Let me spend 1 minute talking about it. 5.21 in short says, hey, what is the net force on the fluid? Okay, well, it's possible that there are contents within this control volume that essentially stay in that control volume. That's rough, by the way, but you could think about them as staying in that control volume and change in linear momentum, that there's some sort of change of that going on. And then another thing that could be going on is that there could be linear momentum flow in and linear momentum flow out. And if we want to get the net force on the fluid, essentially kind of going through the control volume or in the control volume, what we do is we take these two things and add them. Very rough, okay? I wish I had time to make it more precise. But what we're going to do in our class is we are going to do steady state, okay? And so the mathematical expression of this is pretty complicated because it involves some good integrals to express things clearly. But 5.22, we can express if we assume we're at steady state, okay? Steady state, all right? And what steady state is going to mean that the stuff that's actually in that control volume is not going to change in linear momentum, but stuff that's passing through, it can gain linear momentum or it can lose linear momentum. And at steady state, this term right here is going to drop away, okay? So for ME120, we're going to do the steady state cases, which is most likely what you would do out in industry if you were doing work, okay? Then we can express it very succinctly. We can say that if we're doing a control volume analysis, the net force on the control volume, which would be the net force on the fluid passing through our device, okay, is the difference between, is basically how much the fluid's linear momentum flow changes as it goes through. And that can be expressed mathematically is m dot v out minus m dot v in. Okay, and we can have multiple streams out and multiple streams in. To express it, to be pretty clear, we should do it this way. In general, what we're going to do is we're going to do m dot v out minus m dot v in. Okay, and that's going to get us the net force on the fluid passing through the control volume. And let's finish off class by practicing that a bit. Okay, I think we have time for 3 examples. So this first example is a U-bend. Okay, so this would be part of a piping system. There would be piping over here, bringing this water in, and then it makes that 180. This is a 180-degree turn, and the water ends up going that way. Hey, the water that passes through this control volume, what's the net force on it? Now, of course, if you look at the book, if on a detailed solution, they're going to do these dash lines to indicate the system boundary, and that's good. I like that, but I'm going to not really emphasize at this point. At what boundaries does the water end up crossing? It crosses this boundary here in and this boundary here out. Let me write the formula on the board and see if you can finish it off. The net force, okay, on the fluid going through a control volume is going to be the sum of all the m dot v outs minus all the m dot v ins. Go for it. All right, this one takes a little bit of thought. I mean, first of all, a first thing to look at is say, hey, over here, is this in or out? This stuff here is in, so we got that stuff there. But we don't have, it doesn't look like we have out, okay? By the way, I should have said that this is at steady state. So if it's at steady state, what does our in-out analysis say for mass? Mass flow in is going to be equal to mass flow out. That's section 5.1. So what mass flow has to be coming out here? 5 kilograms per second. Okay. How fast does it need to be coming in and out the outlet? Well, again, you don't need to write this down, but hopefully this reasoning will eventually, with practice on the homework, become pretty automatic. We can say if m dot in equals m dot out, that rho v a in is equal to rho v a out. A little bit of a poor job on my part, but in this case, we can. I meant to say that the pipe was constant diameter. That means the area in is equal to the area out. Okay. If it's water, okay, water is incompressible, so density in is equal to density out, and so then that would mean that the speed in is equal to the speed out, and so that's also 4 meters per second. Okay, so you got some more information. Once again, pause and see if you can finish it off on your own. Okay, so we can finish this off just getting the numbers up there. This out is 5 times 4, that's 20, but we got to be careful. It is momentum flow is a vector, so this is 20 to the right, and if we made our positive x direction to the right, that would be plus 20. Sorry about the pen, I'll switch pens in just a minute, so that's plus 20. I haven't done units yet, we could do that at the end. Okay, how about in? That's 20 in, but that's to the left, so it would be negative 20. So we need to be very careful. This would be minus a negative 20. Okay, so our answer is plus 40. Okay, what kind of units? Kilogram meters per second squared. That's how we do momentum flow, but that can be as in newtons. And so what that would mean in this case is this water, there has to be a net force on it to the right of 40 newtons to have it make that turn. Hey, if you got 0, then you might get 0 if you weren't careful about your numbers, and that wouldn't make any sense. You know, if water's going to be turned, there has to be a force on it. So this calculation gives you the correct value. All right, this will be good enough. This will be our last example. Let's go ahead and figure out the net force on that water. The net force on that water. It is entering an elbow, a 90-degree turn, a constant diameter elbow. Okay, H2O, I'm sorry about my writing there. It's going pretty fast, 5 meters per second, nearly 16 feet per second. And the mass flow entering is a lot, a fair amount, 10 kilograms per second. What is the net force on that water going to be? Okay, the numbers here are really easy, but we got to be careful because we need to think about vectors, okay, or direction. So if I were to maybe go ahead and do that control volume drawing over here like this, okay, if we think about it, the N is going to be 10 times 5, which is 50, and the out is going to be 50, okay? So if you're just not writing this down with not really understanding it, m dot v out minus m dot v in, you might get the net force is 0, but there's going to have to be a force on that water to make that turn. So 50 minus 50 isn't really right. So we'd have to do a vector type calculation, all right? And one way to approach it is basically to do out minus in. So out is up here like this, okay? In is a vector of 50 that way, but if we were to do minus it, subtract it, okay, that would be essentially plus the opposite of it, so that you could have a vector here like this of 50. So this is the in, and this is minus the out, okay? And if you add those, essentially take the sum of those two vectors, you get something like that. Okay, and going through the mathematics, that would just be the Pythagorean theorem. So 50 times the square root of 2. I get that this is 70.7 newtons, okay? And there's a force that way, at that angle. And if you think about it, that makes sense. How would you need to push on this water to make this turn? Well, there essentially would need to be a push this way to slow it down, and a push this way to make it move vertically with a net overall force like that. Okay, hey, another quick spin on it, and that will be good enough today, all right? What we're gonna see when we do these two-dimensional problems is we can actually write a force problem in the x direction and a force problem in the y direction. And probably a force equation. So let me write that up there just as a preliminary for something that's coming. We can take our theorem, sometimes it's called the linear momentum theorem, to figure out forces on control volume, and we can write an x equation, which would be the net force on the fluid going through the control volume in the x direction is equal to m dot u out minus m dot u in. And then there'll be a corresponding one in the y direction. Let's do the x direction first, okay? In the x direction, do we see any flow in or out in the x direction? And we see flow in. We don't see flow out. So this would be m dot u out would be 0, okay? M dot u in is 50, okay? And so we get a net force in the x direction of 50 newtons to the left. And hopefully that makes sense to us. Basically, hey, what does the push on this water need to be to stop it going this way? It's got to be the left. Okay, let's finish off with the y direction. Net force in the y direction is not going to be m dot u out. It's going to be m dot v out, where that script v stands for the vertical component of the velocity, minus m dot v in. Okay. Okay, is there any vertical in this picture? Absolutely here, and that's out. So there's 50 out. How much vertical in is there? None, so minus 0. So we have 50 newtons, and that's positive or up. So another way of putting what I just did a little while ago, that 70.7 newtons, is say, hey, there are two components to the force on this water. There's a horizontal component to the left, and there's a vertical component to that. All right, well, that's good enough for a start on chapter 5. Hopefully where you're at right now is you're working on homework number 4, getting a little bit more practice with the Bernoulli problem, and also get with that vector calculus. And I'm going over now to meet with anyone who wants to talk with me during lecture. Hopefully I'll see some of you guys there during lecture hour, and I'm going to be working on Thursday lecture and hopefully get that posted soon.